Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's a pleasure for me to welcome back Sylvain Parry. He visited us actually about 8 months ago. Sylvain is from MIT. He's a postdoc there. He's working with Fredo Douin. He has done a lot of work, very interesting work, in 3D reconstruction from images. He has done hair modeling, and currently he's working on computational photography. And today he's going to be talking very interesting stuff on bilateral grid and image segmentation.
Thank you very much. So my talk will be about an extension of what I presented to you last time I visited. And there will be two parts to my talk. The first one will be about the bilateral grid, which is a new way to represent images. And the second part will be about image segmentation. So this work about the bilateral grid will be presented this summer at SIGGRAPH, and it's I had the pleasure to work with Jiawen Chen and Fredo Douin on that project. And our motivation is that for photography, very often you do operations that are edge-aware. And what do I mean by this is, for instance, for tone mapping, where you have this problem when you have an HDR picture where the intensity range exceeds the capacity of your display. You can apply a smooth tone mapping operator to bring back the intensity range within the capacity of your screen. But if this operator is smooth, you get problem of halos, as you see here, near strong edges. So in practice, it has been the notion of edge-aware remapping has been introduced by Jang Toblin and reused later by Fredo Douin. And you see that you obtain a solution without any halos by applying a piecewise smooth exposure correction to your initial picture. Another domain where it's interesting to get edge-aware operation is scribbling, and that has been introduced by various people. But for instance, there's a lot of work that has been done here where you get a picture like this and you loosely scribble a region where you're interested, and you want to extend this scribble to define selection, influence map, and you want this interpolation to take into account your image structure. That you see the result here. There's discontinuities in the selection map where there's discontinuity in the picture. Another domain where edge-aware operations are interesting and piecewise smooth transformation is useful is abstraction, where you start from a photograph and the algorithm create an abstracted version that looks like a cartoon, where you have large colored regions that are almost uniform, and you add some lines on top of it to give it this cartoon effect. And all these work with the same notion that you want to smooth your picture, or you want to do something smooth but still be discontinuous where the picture is discontinuous. And in that context, our contribution is to introduce the bilateral grid, and that's a new way to represent images. And this data structure makes it easy to achieve such type of operations that are piecewise smooth and edge-aware. And another advantage that it's hardware friendly. It's easy to map this algorithm on the hardware using this image representation. So the rest of my talk on this point will be organized as follows. I will first define the grid and show how we use it on a simple example. That is the edge-aware brush, and I will show you what I mean by this. Then I will show you a few more operations that can be achieved with that data structure. I quickly describe and discuss how this we map this algorithm onto the hardware, and then I will show you a series of applications. So the bilateral grid is a data structure that we first introduced last year at ECCV, and we introduced it as somehow a byproduct of some work we have done on the bilateral filter. And today I will show you that this data structure is useful beyond just bilateral filtering. And what this grid is about, it's a 3D grid. The first two dimensions are the x and y dimension of the image. The third dimension in the intensity. So here's just a simple 2D example that I will use. So in that case, the spatial is just 1D, which means that we have only an x-axis, and what we will call the range axis is related to the pixel intensities. It's real volumetric representation in the sense that we store data everywhere in this 3D grid. It's not a 2D manifold. We can discuss that later if you want, but mainly that's a grid with data everywhere. The resolution of the grid is coarse. If it's something to give you a range of numbers, this grid is 32 by 32 by 16 or 64 by 64 by 32 samples. So it's not at all about 8 megapixel picture. Even if the picture you're dealing with is very large, we still work with a coarse data representation. And each node of the grid can store virtually any data type. Very often we store an intensity or homogeneous intensity, and I will just describe a bit later what I mean by homogeneous intensity. So that's how we define the bilateral grid, but I think it will be more concrete to see how we use it on a simple example. What does it mean, all that concretely? And I will describe it on what we call edge-aware brush. So an edge-aware brush is a brush that, very similar to what you do in Photoshop, you can brush anywhere, but the effect of the brush does not cross edges. So it looks like this. So for instance, here we have a brush that changes colors. The user click and just change the color of the door. But as you can see, the user is not very careful. But still, the brush stops at edges. We don't brush over the edges. We change the color, but it does not bleed on the wall. So that's what we call an edge-aware brush. And I will show you how we use the grid to achieve this effect. So we start from a signal, which is the position, the intensity of the pixels, and that's just a plot of the intensity as a function of the pixel position. And we have a grid under this signal somehow, like overlaps this signal. And when the user clicks, we look up where it is at the intensity of the pixel and just splat a small Gaussian. It's the very same type of painting that you do in Photoshop, but here we do it directly in the grid. We do a very smooth editing of the grid, and the user click here. We add a small Gaussian in the grid at this location. So we create these values in the grid. The dark gray values are the default values in that case. And at the end, we obtain some values that define where, in that case, this is the region where we want to change the color. And we have an influence map that says here, change the color because it's a high value. Typically, that you can see that as an alpha map. And the way we extract these values is by reading the values of the grid that are under the plot. So does that make sense? That we have the plot, and this plot is 1D, but we have a 2D grid under, and we just read the values that are in the grid at that location. And an interesting property is that we have a discontinuity in our input signal here, and we retrieve a discontinuity in the output signal here. But you can see that the values that we store in the grid and that the user has painted are very smooth. Here, that's a very smooth function, but we read at very different locations the values. So because we read the values high up here and down there here, even though the transition is smooth in the grid, we read far away the value, so we preserve the discontinuity here. That's how we achieve this effect of edge-aware painting.
Can you explain a little bit more? Because I don't quite understand what you're. When you say you're pulling those out from the grid, but you're measuring the distance to the intensity function. I mean, you're measuring the height of the intensity function, or how are you using the grid pixels? I don't really understand that.
Okay, sorry.
Somebody else. Oh, cool. That's what I'm doing. So. Okay, cool.
Oh. Up here. So, sorry.
It's not the length of the yellow lines that you're talking about.
No, the yellow lines are just to. So that's a 1D picture. That's a slice in your image somehow. That's a plot. And
so
what?
You construct the blue lines how exactly?
So we have a grid that is a dense structure where we store values for any position, but also any intensity value. Not only the intensity values that are inside the picture,
Right.
which means that we will have values here, for instance, even though there is no image value here. And this grid is what we see here. That's the blue grid. And
But that's just initialized to being a homogeneous value, is it?
that's initialized to be gray values, which correspond to this dark value here. Everywhere I should have done an animation, but we are still working on that material for the final presentation. We start with uniform gray, dark gray values, which correspond to uniform low alpha values.
Okay.
So we can say that this is 0. This dark gray is 0. And then the user click at that image location, that yellow dot. What we do, we look up the intensity value corresponding to that
All right. Okay.
yellow dot. In the centered at that grid position, we splat a Gaussian there, a very smooth Gaussian.
Mm-hmm.
We put that Gaussian there. Then the user click here. We look up there.
Right. Yeah.
We splat a Gaussian around. And this is edge preserving because when the user click near the border, we splat a Gaussian here around this point. But as you can see, this Gaussian is high in the grid, which corresponds to high intensities. So the other side of this edge correspond to darker pixels, and these darker pixels are not touched by these Gaussians, which is centered here.
But in your video, your animation, your mouse was moving over the white part of the wall too. So then it would be, if white is the low part, then you'd be dropping stuff.
So what happened in the video, we have a system that's slightly different. That the first click, as long as you hold the button down, we don't change the height where you're painting in the grid. Here, that's a situation where the user click and release, click and release. In the video,
basically selecting a target color in the image
Exactly.
that affect things there.
Exactly.
Value.
I guess I was unclear about how you then take that grid and then convert it to the blue plot on the right.
So then, is that clear how I paint inside the grid? So now, how do I get the blue part on the right? I need a value for each pixel, each location, x value. I want this alpha value. And the way I do it, if I want to know the value corresponding here, I go in the grid at that location, go up where the plot is, and read the grid value under. I read
Where the plot is.
exactly where the plot is. So when I need to know the value here, I go here, go up, here, read it's dark gray, so it's a darker value, it's a 0 alpha.
Okay.
Is that better?
Yeah, that's better, yeah.
Yeah, I'm sorry for the first version, that was confusing. And here, there is, again, to insist, the property of this representation is that when we extract, and that's a very powerful operation that makes everything works well, is that extraction scheme where to know the value here, we go and read there, which means that where there's a discontinuity, we read two values that are far away. So the grid is smooth, but we obtain a discontinuous result because we read at different locations. And when there's discontinuity, we read values that are separated. So even though there is a slow transition in the grid, we put a distance between the 2 points and introduce a discontinuity.
So when you actually do a mouse click and splat,
Yeah.
do you add the contributions or you take the max of the contributions?
So I think it depends. You can have different mode. In Photoshop, you have the, what is it called, the hairspray mode where you add, and I think the brush is a max. You can imagine different modes. I think here we take the max because that's a brush, a hard brush. But you can imagine also the hairspray that you can, wave around and get more and more effect as you come back. So now I will present a few other processing that we can do in the very same spirit. So the first one we can do is what we presented last year, is a bilateral filter. So the bilateral filter starts from an image. So here again, that's a slice of this picture. The first thing that we do is create a grid that represents this signal. And the way we do it is everywhere we have a pixel, we put the intensity value in the grid under. That's an homogeneous value, which means that each intensity value is attached to a weight. And when we put blue value here, it means that the weight is 0. So everywhere you have value, but we have only weights only where we put pixels. So that it's not clear. We start with a grid with no weight, 0 weight everywhere, no contribution. Each time we have a pixel, we look at the position as intensity. We look at this grid cell that corresponds to this position intensity and add the intensity there, and we put a unit weight attached to it. We say this pixel has a weight 1, and we add it in the cell. It's just we bin pixels this way. We add intensity and count how many pixels we have put there. So that's what we see here. Most cells remains empty, but there's some cells that store some intensities in there and some pixels. Then the bilateral filter is about, we just blur the grid. So we don't change the signal. I just show it to remind you where is the signal in the grid, but it's not important there. We blur this signal, which means that we have this blurry representation where the blueness of the color corresponds to the weight. So it means here we have 0 weight and we have a transition values that are with lower weights. It's just a very standard Gaussian blur, something very simple to compute very fast. And what we do at the end is again the same operation. To know the value at this location here, we look at the same location, go up, read the plot, read the value under, and it's an homogeneous value, which means it's an intensity attached to a weight. So we remove the homogeneous component from that, and that gives us the intensity value that we see here. And that was a result of our paper last year to prove that this operation in the grid, where basically you just blur the grid, give you the result of the bilateral filter. And as you can see here, we still have a very smooth signal in the grid, but we still preserve the discontinuity because we read at different values here and here. So another operation that we can do is edge-aware interpolation, which corresponds to the scribbling interface. So in that model, the user clicks somewhere in the picture and give a constraint. So the user chooses a brush, for instance, black, saying that this region will not be selected. Click here in the picture, we look up the signal, add a constraint in the grid at that location. The user click here, we go up, look up the signal as a constraint in the grid there, and we do that each time the user click. Here the user says this part should be selected. So it select a white region. We go up, select, put a constraint in the grid. We solve a smooth interpolation problem, which means that we preserve this constraint and minimize the gradient variations over the picture. Very smooth interpolation scheme, just a Laplace one, no edge notion, edge preservation notion involved in there. Then we apply a sigmoid because the idea is there we have too many intermediate values. And in that problem of scribbles, you always want a lot of white and a lot of blacks. So we force this, we just remap the value here to get a lot of blacks and a lot of white values. And again, the same operation. To get the values at this location, we go here, up in the plot, read the value under. That gives us the result that we see here. And even so, we solve a smooth interpolation problem in the grid. We have a discontinuity with the very same property that these 2 points are far away in the grid. So this signal remains smooth, but we get a discontinuity there. And we account for the edge at the last time, at the last step. So it makes this step very easy. We don't have to worry about edges at that point.
So how do you solve the Laplacian conditions like that?
So we use a multi-grid implementation here to solve the Laplace problem. So I think that an interesting discussion that this interface with scribbles has been proposed before, including people here on very. And I think the difference between what we propose and what has been done before the technique is very nice and can be finely tuned on per pixel basis because you look at all the pixels and decide what happened, how you propagate and interpolate your values at each pixel. In comparison, our approach has worked on this coarse grid, so we don't have this flexibility at the pixel level. But what is nice is that the resolution at which we solve the problem is independent on the image resolution, which means that we can do this interpolation for very, very large pictures like 8, 10, 15 megapixels for the very same cost that you would do a small picture because we work on the same grid. And that grid that I told you has typically a resolution of 32 by 32 by 16, which makes about a couple of thousand samples.
It still limits the resolution at which you can make a change.
Yeah, exactly.
Like if you never want to change just 5 pixels or just make 5 pixels blue, then you can have it as large as you want. But if you want to have it that's fine,
if you want to be,
you do need a bigger grid, right?
Exactly. So what constrains your resolution is how close you want to be able to put constraint, either in space or in intensity. Or if you want to be able to make difference of a couple of grade levels, then you need a lot of resolution. But we found that in practice, not what people do. Like either it's very rare that you put scribbles that are both very close in space and very close in intensity. Very often you scribble on the background and on the foreground. That's a typical use of that kind of approach. And in that scenario, you very quickly get 10, 20 grade levels of difference, which means that you can't downsample by that much your grid.
Do you think it'd be possible to take your approach and apply it to an octree?
Yeah, maybe the
representation to handle that. I mean, if somebody wanted to do that.
Yeah, you can do it in practice. You can go up with a resolution. Here, Jawen is still working to make the performance better for that specific problem with multi-grid. It's not that fast, and Rick would tell like we should do locally adaptive here, and he's working on it. But it's not memory is not an issue actually. That we can go fairly high if we need to. And the other part that is specific to our approach, that the optimization problem that we solve is extremely simple because we don't take into account edges at the optimization time. We take into account at the extraction time, which is comes later and is decoupled from optimization. And the last application that I will show you is local histogram equalization. And this application is about remarking that for such a signal, if we want to increase the contrast, here we don't use the full range of intensity that is available. Like obviously this part could be stretched to go down, and this part here could be stretched to go higher to spread all the intensity range. That could be very useful for medical imagery to increase the contrast at each point of the picture. That the full picture covers the full range, but locally we don't use the full range, so we would like to use the full range. For that, we create a different grid where each cell counts the number of pixels that falls in it. So if you just look at one vertical column, this is an histogram of the pixels that falls in this region of space. As you can see here, we just count how many pixels falls in each of these cells. So these are just local histograms of the picture. What is the histogram of all the pixels there in this column, and we have these histograms. We run histogram equalization of each of the column, which means that we have this remapping where at the bottom here it's black, at the top it's white, and this covers exactly the spread of the pixel values in each column. And again, the same operation. To get the value here, we go here, look up the signal, read the values in the grid under, and we get this new signal that use the full intensity range at each location, that we spread, we make the best possible use of the intensity range everywhere in the picture.
How do you handle boundary issues on this? Do you do a smooth blending?
So actually, I wanted Jawen to do a smooth blending, as you said, and we don't do it, and it works very well. And we don't do it, but it works very well Because at the end, when you, for instance, you are here, and let's say you don't fall exactly at the center of the bin, but between, slightly between both. So this value here is actually a linear interpolation between the value of this bin and the value of this bin. So the linear interpolation is enough to remove the aliasing effects that you described. You will see the result is completely invisible. As I announced, it's hardware friendly. So here a few details how we implement it. The 3D grid is unfolded onto a 2D texture. There is a problem to create the grid because fragment shaders are not very good at scattering data, because the operation that we need to do is to read a pixel, look at the value of the pixel, and depending on the value of the pixel, we write at a different location, and that a fragment shader is not good at. So, but the vertex shader can do that very well. So what our algorithm does is to convert all the pixels into XYZ point where the intensity is a Z coordinate, and the vertex shader spreads the points into the grid. And this linear interpolation that we just discussed can be made very efficient by using the texture engine that does a bilinear interpolation, and we have a dedicated shader for the last interpolation. And here's the performance that we obtain on bilateral filtering. And this is the size of the image here. And this is the running time in milliseconds. We tested 3 different generations of cards, so that's the very latest one, 1 year ago and 2 years ago. And here, 40 milliseconds is an interesting bar because it tells you real-time where you can go for real-time processing on videos. And something very interesting is that 2 megapixels here, because 2 megapixels correspond to HD videos. So it means that for HD videos with any card, even somewhat old 2 years ago, we can do real-time video processing on HD video. We can also push forward for large images that what you typically get for an SLR. This other plot shows here that the size of the kernel that we use for the bilateral filter, and that's again the time in milliseconds. So I discussed recently with David Lübke from NVIDIA. He told me that these two are very likely to be bugs in the driver, these two peaks. But what is interesting is the latest generation give very consistent, almost constant running time for any settings of the bilateral filter.
What are those peaks?
So these peaks, we measured them. We just vary the size of the kernel, and for some unknown reason, we have peaks in these 2 cards, which the performance drop very poor. It becomes very poor for settings of about 60 pixels. It's completely no control. We don't know why this happened, but we have these 2 peaks that appear, and a peak around 30 pixels. And I discussed with people from NVIDIA, and I want to send them this to see what happened. And it seems that first we were thinking that we eat some cache, something like that, but they say it's more likely to be even a bug in the driver. Or I don't think that's very important somehow, because if you go away from this bad region, you get again nice performance, and the latest generation doesn't have this issue anymore. So these 2 cards will be soon.
When you vary the spatial sigma, does your space resolution?
So this one is
change?
no, it's 8 megapixel.
Right. No, but underneath the first diagram, you have space resolution equals 16 pixels.
Yeah.
That means your little samples are every 16 pixels.
Exactly.
Right. But when you have your spatial sigma, are you talking about the samples or about the Gaussian blur sigma?
So we use that's the value for both, actually.
Oh, I see.
So that has a very nice property that your Gaussian, once you have done sample, has always a unit variance, because you sample every sigma.
Okay.
So you have one sample is always 1 sigma.
Okay. And that's a dense enough sampling in your experience to avoid aliasing.
Yeah, that's all the results that I will show you are all obtained with that approach. And so to give an idea of how fast this is compared to CPU implementation, that's 2 orders of magnitude faster than the same, our approach of bilateral filtering applied to a good CPU, a latest generation CPU.
And in your diagrams, you've always had range as sort of a scalar variable, intensity, right?
Yeah.
But in your video, you were doing color-based painting.
So what happened in the video, the color-based painting was actually only looking at the luminance discontinuities. And that's a limitation of our approach.
Okay, so if you had some sort of moderately dark red as well as the blue, that would
Exactly, then we bleed. And in series, there's nothing that prevents you to do a 5D grid where you have X, Y, and the color attached to it. But the limitation that the grids are to be really large, and then the GPU is not very useful anymore to deal with that. There's issue with memory and issue with processing. The neighborhood are large. 5D linear interpolation start to be costly. I can advertise, we have a tech report online that is all about CPU implementation, but that studies this aspect of the bilateral filter. So on the CPU, you can do a 5D grid, it's easy, and we show how the performance drops. It's still faster than a brute force implementation, but then just the GPU is not, you don't have this nice.
So I can see for image-wide operations that this is great because
Yeah.
it's super fast and everything, right? But now let's say we're back to the painting example where you showed in the very beginning. Is there really a big win on that? Because the amount of CPU time it takes to even a 20 by 20 pixel window or however big that brush was, it's not that computational.
No, I agree.
Okay.
I completely agree. You can, for something like the brush, I'm sure someone good with the CPU could make it happen with the same types of speed up.
Yeah. So do you see an advantage in that scenario? Is there?
I think what is nice is that we can handle very large picture and all that, and that's easy to code. But yeah, sometimes you can achieve the same thing with the CPU implementation. Especially the brush is the most likely one to be useful because you do something very local and you do know where it is. So I agree, the brush one, probably a CPU implementation, would not be that fast, but for the users that would not make a difference.
Well, suppose if you do a flat fill, like click and then it fills the whole thing up to the edges, then it would help, right?
Yeah, that's hard to be more like the scribble, but it's true that the scribble. But yeah, you already have float fill somehow in Photoshop. In Photoshop, you can set these fuzziness parameters that tell you how well, what is an edge, what is not. And that one is fast, I agree.
But float fill might actually jump across the edge. Because sometimes when you do float fill, you might have a skinny edge that you don't want it to jump across that skinny edge, but since you're kind of blurring out, it will jump across that skinny edge. So, does that make sense? Like two black areas with this thin white line in the middle.
Right.
Your method might jump from this black area to this black area.
So our approach is clearly, that's always a big discussion. Our brush cross thin edge. And I will show you in the result video that sometimes you want to cross thin edge. If you don't want, there's other tools that don't cross thin edges. It's really application dependent, and it's two different behavior. Both of them are good. Ours cross. Clearly, our approach crosses edges. So some results. So here, the local histogram equalization applied to medical image, that's X-rays. X-rays are equivalent to HDR images. There's a lot of data that you get at each pixel. And we compare to MATLAB, and we don't get exactly the same result, but we don't know exactly what is doing MATLAB, but in essence, qualitatively, we get something very close, and that's really fast. We get 1/10 of a second to get it instead of 1.5 seconds. And now I will show you a video with more results. So this application is a direct use of the bilateral filter. So here you see the parameter space of the bilateral filter, and the user will move this red circle that defines the space value and the range value of the bilateral filter. And here you see the result, the filtered image or the input, and that will be written here. This picture is large, 12 megapixels. And we do a full update each time of all the pixels. Even so, we don't sample it to show it on the screen. The full picture is updated each time.
Are these pictures of the prototype?
Yeah. Oh no, here. So we change the parameters, and as you change the parameters, you see the effect on the image. And here we zoom, and we do a global update, not only the small window here. And we feel that's really useful to set because you get real-time feedback, so it's easy to find the right parameters. Here we implemented last year paper by Holger Windmüller. where you start from an input video and the output is stylized with a cartoon style, which means that we make a piecewise smooth rendition of the color and we add lines across strong edges. And this is an HD video. This corresponds to 1 megapixel, and the frame rate is 65 Hertz.
So it processes the frame independently, right?
Each frame one by one, yeah. And here, what we did, since we were at 65 Hertz and these videos are 30 Hertz, we can add Duke de Carlo's idea that you have a point on focus somewhere in the picture where you have more details and far away you have less detail. So here the mouse pointers indicates where there is more focus. So as we move the mouse pointer, it reveals details near. And the way it works is that we have this, which is a distance map, starting that indicates the distance to the pointer. And we make an adaptive distance map by cross-bilateral filtering this distance map with the picture. So you have this effect where the level of details depends and adapts to the video content as we move.
Spatial sigma does?
Sorry?
Is it the spatial sigma that's varying?
So here, yeah, the spatial and the range sigma they are we double each time, I think, if I remember.
Then doesn't the grid density have to change?
Yeah, but we recompute. It's fast enough that we can compute all the bilateral filter within the time, the frame. Between the time between two frames, we have time to compute all these bilateral filters. Plus to compute these cross bilateral filters that adapt the distance map to the result. And that's again the so this part is what we presented last year, where we have a model photograph made by an artist. So this picture is by Ansel Adams. And we analyze this picture and transfer its style to videos. And here the input is gray with little detail. And we have a more contrasted output. And this pipeline is based on the bilateral filter, so we reuse as the input as the stylized version. And something that we feel is really useful is that all this is parametric, so we can change the parameters on the fly as the video plays. So for instance, here we change the brightness and change the texture level of the video in real time. That's again the painting algorithm. That's the same thing that we have shown you before. So here, when the user clicks, we lock the height in the grid where we paint. So that's why you can even go over white region without painting.
That's why some of the grill parts just don't get painted.
Exactly.
I see. So both the blue and the red are being painted.
And so here's the user click, and then the button is whole. We are working on a better video when we see also the button at the same time to indicate what happened with the button. We can use the same interaction for local tone mapping, and this one we'll see why sometimes it's useful to cross edges. As the user click and can brush over the fence without modifying the fence because we cross these edges. That's a typical example where that's beneficial to have this behavior. So we go here and you can just go over the windows because here the button is down always, so the windows are not edited. And here's at the scribble. So black indicate we don't want to touch, and white indicate we want to edit the region. So we change the color. The user is not happy because some part is not selected at the scribble. And again, that's a 2 megapixel picture which is edited each time you add a scribble. So that's our application. So to summarize this part, I presented the bilateral grid, which is a new image representation that is independent on the actual image resolution. The powerful part is really when we slice this grid, when we extract the result from the grid, that's where edge preservation occurs. And it's nice because it makes a lot of 2D edge-aware processing becomes smooth processing in this 3D representation. And it's hardware friendly, which enable HD video processing and on-the-fly adjustment of all the parameters, which is, I've not shown that yet to any professional of video, but I'm sure they would like it a lot. So now I will show you another work that I've done that is also linked to what I presented last year about the bilateral filter, but this time we move toward image segmentation. This will appear soon at CVPR, and I've worked on this project with Fredo Durand. And low-level segmentation is about grouping similar pixels. And here's the input and here typical output. You have groups of pixels that looks similar. And that's a very useful process. Like, for instance, some approaches for video segmentation, video processing that have been done here. You pre-process your video, get groups of pixels, and you deal with these groups of pixels instead of individual pixels. So it's faster. The following algorithm is faster. It can be useful for analyzing your photograph, and for instance, Bing has worked on segmentation of vigneting correction using segmentation. So you analyze groups of pixels and the statistic in this group. And Duc DeCarlo used segmentation for abstraction, which is exactly what I show you with a bilateral filter, but you can also do it with image segmentation. And there is plenty of algorithms to achieve image segmentation about graph, mean shift. That's an open question. I'm very happy to discuss it. How do you choose your segmentation algorithm? It's so far everyone has his own favorite algorithm. And mean shift is one of the popular options because it's simple, fairly easy to tweak to your own needs, and it's fairly well understood. There's a number of theoretical studies that characterize exactly what you compute with the mean shift algorithm. So the rest of my talk will be first describing this mean shift algorithm. Then I will present our approach that is based on the notion of point density. And I will finally introduce a new interpretation of this algorithm using a topological framework and show some results. So the first thing you do for mean shift is for each pixel you create a feature point where you associate the position of the pixel to typically the color of the pixel. You can decide other feature point, but that's the typical feature point that you use, position plus color, and the color is expressed in LAB. Then you start a sequence using this feature point where each new point of the sequence is a weighted average of the feature point according to some kernels that tell you, and I will show you something more visual, but you weight the neighbors, you move to the mean of your neighbors, and do it again. You have a new point, look at the mean of your neighbor, move again. And you iterate that until you converge. And the result of the segmentation is the segment are all the points that have converged to the same limit. So let me show you, I have an animation. So here is a simple 2D feature space. All the white dots are feature points. Yeah. Okay, so that's the feature point. We will segment this feature space this way. For this point, we use a Gaussian window around it, and we compute the average of all the points in this. This defines a sequence like this. This converge. Actually, we do that for all the points. And we group the feature points that converge to the same limit. That's the way mean shift is defined. And actually, there is a known result about this algorithm that this sequence, these trajectories that we have seen correspond to a gradient ascent on the point density in feature space. And it's known, the intuition is really that these points are attracted by where there's a lot of points. And it's known that if we use the Gaussian windows, as I show you, the density is computed using a Gaussian estimator in feature space. Let me show you what this corresponds. So that's the same feature space, the same iteration. Blue means sparse region, red means dense region. And as we can see, this trajectory goes where there's a lot of, where the density is higher. Actually, we can see it in 3D, that this trajectory really go up on the density function. So this is a plot of the density function, and these are all going up. And here, that's an horizontal plane to give you the intuition of what we will do. This plane is at a constant height, constant density, and all the points that are above this plane, I know for sure they will converge to the same local maximum. That's guaranteed. We don't need to make all the iteration to know that they will end up at the same local maximum. They are above the plane, and there's only one local maximum there. So that's a known result. And as we go down, we will see that this applies to other. But as we see, there's some merging that occurs. So we will discuss that point. But the intuition of our algorithm that we will compute this density function and extract the modes of this density function, because the modes correspond to any point in a mode will always converge to the same maximum. So if we know the modes, we don't need to do the iterations, and we directly get the segmentation. And something that is interesting is to look at this plane, but again from above. As the plane goes down, we see some connected components that appear. That's the small part that I've shown you that was above the plane. And as we go down, we have another small part that corresponds to a maximum and another one. So that suggests the topology of these parts that are above the plane are interesting. And the way it works is that we will study this topological the topology of this effect. And as we move further down, there is some mergers that occurs. And some features remains distinct very long, but some merge faster than others. And that gives us a notion, an intuitive notion somehow of the importance of a mode. If a mode creates a component that quickly disappears, it's not a very important mode. But if the mode creates a component that survives very, very long as we move the plane down, that's an important mode. That will give us an information about each mode and let us construct a hierarchy. So first, here, what we do, the algorithm that we propose is first to compute explicitly the density function, then extract its modes, and then build a hierarchy using Morse theory, which is exploiting this notion of plane sweeping over the density. Computing the density function is something that can be done fairly easily, because the density function, if we use a Gaussian estimator, it's a band-limited signal, so we can use a coarse sampling of the feature space to compute and represent this density function. And furthermore, it's a Gaussian, so we can use a separable kernel to make the computation efficient. So at the end, we just put a grid. We put a grid in feature space, a coarse grid, and compute a Gaussian, put the point in there and compute a Gaussian over this grid. Then we extract the modes, and that's very similar to existing algorithms such as watershed, or in topology, it's named filtration. And the objective of this step is to put a label at each grid node. We have this grid in feature space, and we want to put a label that says this is a mode 1, and mode 2, mode 3, and be able to label each of the grid. And the way it works, we go from top to down, the very same way I've shown you this plane going top to down before. And here, there is a 1D example how it works. So here, that's my space, my feature space, and I have a grid with regular sample. And I have the density of each node of the grid. And I go top to down. So the first point that I look when I go top to down, it's a global maximum of my feature space. So I know this is a new that's a maximum, that's a new mode, and I give it a label M1, my first mode. Then I go down and I see this new point, and I look around, no other points nearby have been labeled. So this one is the highest of its neighbor. So that's a new local maximum, and I give it a new label M2. Then I go down, And this one has a neighbor that has already been labeled, and only one label. So it's part of this mode, because I know if I start here and I go up, I do a gradient ascent, I'm sure that I will end up here. So I just copy this label here. And sometimes a node has two or more labels, like M1 and M2. So this one is a boundary between two modes, because here it's unclear if I go up, if I will go there or there. So this one, I put a boundary, a special marker for boundary. This algorithm to extract the modes is very simple. The first thing that we have done is to sort the green nodes by density, top to down. And for each node, we count how many labels are among the neighbors. If there's no label assigned already, then we create a new one. We know it's a local maximum. Give this new label to this grid. If there's only one label, we are sure that going up will always end up in this label, so we copy this label. And if there's two or more labels, we know that we are at a boundary between two modes, so we put this special marker. And that's it. That's a very simple algorithm that sorts the nodes and count how many labels are around. So that's a very efficient very simple to implement and very efficient. The last point to see is that we have these boundary markers that correspond to nodes. So all the pixels that fall in such a bin are not classified because there's no label. And what we do is we start the iteration process for these points. So we start an iteration, move up along the density, but we stop as soon as we reach a node where we have a label. So we don't have to go all the way up to the local maximum. We stop as soon as we enter the previously classified region. So yeah.
This requires you to have a discrete density space, right?
Yeah.
And so, how discrete is that?
Sorry?
Does that make a big difference to the results? Like how discrete that is, I suppose.
Yeah. So that makes a difference only.
To, iterate. I don't know.
Yeah. So first, actually, we have a discrete, but we do linear interpolation between samples to get something that is linear, continuous and not discontinuous. That makes a difference. I can show you in the result, but that creates boundaries that are not important. And with the latest part, we will be able to find these weak boundaries, and the hierarchy quickly removes them. Actually,
isn't this sensitive to noise? Or these classifications? Well, because once you put noise, there are a lot of peaks.
Exactly. So that's why we want to build a hierarchy. And this notion of the topological notion that we have later take into account the noise to define the importance of a mode. So I think it will become clear in a few slides. So just this system, just have shown you this algorithm that counts, sort the points and count the neighbors, is able to classify about 80% of the pixels. That's what we see here. The black pixel remains unclassified. They are at boundaries. So we start an iteration for them, and we fill in all the gaps, and we get this result that we see here. But in practice, there is much fewer iteration needed. Even for these points, there's few iteration compared to a full sequence that goes up to convergence. So this compute one level of hierarchy. We have a full segmentation, but actually we can go further and interpret what we have done in terms of topology. So just a quick background about topology. It will be all that is about Morse theory, and Morse theory relates the topology of a manifold to its critical point. And critical points are the points where the density is flat. So in general, you consider a manifold and a height function on this manifold. So here our manifold is a feature space, and the height function is a density. So in Morse theory, we have a manifold, which is here, and the critical point is where it's flat. So it's local maximum, saddle points or local minima. These are critical points. So there is a so-called stable manifold, which are all the points that goes up to a local maximum. So these are two stable manifolds. There is unstable manifold, which correspond to local minima. So this is we have three unstable manifolds in that case. Something that people in topology are very interested in is the Morse-Merle complex, and a Morse-Merle cell is the intersection of the stable and unstable manifold, which means at any point in a cell, if you go up, you end up at the same local maximum and go down at the same local minimum. So that tells you all these points have the same property. If I walk up, I end up at the same point. If I walk down, I end up at the same point.
So a point of inflection is not considered a critical point here?
Yeah. For instance, this point here has nothing special in that framework. The special points are the ones that are flat. There is zero gradient. Morse theory is about thresholding the manifold according to the height function. So you set a threshold and you look at the manifold that is above this threshold. That's really what I show you in that animation with a plane. If you remember, I was putting a plane and looking at the points that were above. And we are studying, Morse theory studies the topology of this thresholded manifold. And there is the persistence. The persistence in that case is the difference between a local maximum and a saddle point between two local maxima. That's the persistence. And if you remember when I was moving down the plane, that's the lifetime. As I move down, I will see a connected component appearing around this point. And this connected component will merge with this other component. So this persistence is how long a connected component survives before being merged to one of its neighbors. So does that make sense, all this notion? So now if I come back to our mean shift algorithm, a local maximum is called a positive critical point because it creates a connected component as I sweep the plane down. A saddle point between two local maxima is called a negative critical point because that's where a connected component disappears by being merged to one of its neighbors. The modes that we have extracted correspond to what is named a stable manifold in that framework, but that's the very same definition, is the very same thing. And we know that these modes are union of the Morse-Merle cells that are being studied a lot in topology. And what's interesting that Edelsbrunner, who is at Duke, has explained how you can simplify such a Morse-Merle cell, Morse-Merle complex, by taking into account the noise. Because he was worrying about what you said. If there's noise, maybe I have a lot of small modes that are not very relevant, and some of them are just, not interesting at all. And he explains that this notion of persistence is a good measure for the importance of a mode. And if you have a small bump, you have a small persistence, which means that this will create a component as the plane sweeps down. This will create a component, but this component will quickly be merged to another one. So you should ignore it because it's not a good one. If you have a component that appear and survive very, very long as you sweep the plane before being merged, this is a good component that you should take care of.
Well, maybe you should just pre-filter, right, based on what you think is the maximum frequency associated with noise.
Yeah, you can, but that's something you can pre-filter your density function, but that corresponds to using a different bandwidth for your mean shift. And that's not clear that what you want. And here, the interest that my point of view is that better to start with a small bandwidth and do a hierarchical segmentation using this criterion of persistence, that merging the ones that should be merged. And so you get not only a segmentation, but a hierarchy. Maybe you're interested in that very small scale, but maybe there's some noise. So you can move up in your multi-scale segmentation, get a level where you're confident, but you can still move upward and get a coarser representation of your image where you're interested in large sigmas, in large clusters. For instance, I remember for your vignetting correction, you were interested to get very large cluster in the sky or something like that to be able to have a lot of pixels to fit your function. So that makes a lot of sense to go very high in that hierarchy to get large clusters. So you will be able to fit very robustly your function. And so how this simplification works, you start from stable manifolds, so the modes that we see here, so 3 different modes. You compute the Morse-Merle complex, which corresponds to splitting where you go up and down at the same point. And every feature that is smaller than a given threshold is removed. So you just merge, remove what is created by these 2 points. So you merge all these together. Now the next one that is not the next feature corresponds to such a high difference, and that's above your threshold, so you don't simplify. And you re-extract the new modes that correspond to this merging again the cells together. That's in spirit what we do, and that's this part 2 and 3 is what Edelsbrunner has proposed to simplify the Morse-Mel complex. And 1 and 4 is what we add because we only care about the stable manifolds. We don't care about the local minima. And what is interesting is that you can prove that we have enough information not to go from here to here directly, still doing virtually that. That we can guarantee that we can go and directly compute from here, simplify this mode, this representation, and obtain directly this representation without explicitly computing the Morse-Mel complex. But the operation that we do is strictly equivalent to computing the Morse-Mel complex, doing Edelsbrunner simplification, and regrouping the cells into stable manifolds. So we can prove that part. So there is several advantages to this approach that is guaranteed to be a hierarchical segmentation, which means that the small clusters are grouped into larger clusters. So it's really a tree of segments. And for instance, if you increase the bandwidth to obtain larger and larger segment, this tree property is not guaranteed at all. So this approach guarantees a tree structure. It's very cheap to compute because as we sweep down and build, extract, label the mode, we just have somewhere to store when we reach a local maximum and a saddle point. And this all we need to compute the persistence. So virtually we get a hierarchy for no extra cost. When we have done the first segmentation, we get everything we need for the multi-scale representation. And furthermore, we can do an on-the-fly simplification, which means that we can go at any level without computing the finest level. We don't need to go all the way down and up again. And for instance, in the case of what's being said, if you're not interested in all the small clusters because they are due to noise, you don't need to go quickly down and then simplify. You can directly go above the noise level.
So, when you're doing mean shift, a naive way of solving this problem is, say you have a big white area, right? It gets broken up into a bunch of little clusters, essentially, right? Is you just look at the mean color of the neighboring segments, and if they're below a threshold, you merge them. That's post-processing stage, which will create a lot of kind of similarities to this. So, what is the advantage of doing this versus the more naive thing that I think people generally do?
So I think here you build upon this theory of topology that tells you that this is meaningful. This has some sense. It makes sense in terms of topology of the feature space. But actually what we propose is to add a color difference term into the persistence because as an application is what it makes more sense to take in. It makes a lot of sense to take into account of both the topology, which is the noise of the height function, and in the color similarity. Because, for instance, your color similarity does not tell you anything about these small bumps, as about noise. Maybe here, this accounts only for the noise. Yeah. So here it tells you if that there's some reason that you should even care about a segment.
So is there a practical example where this plays out and gives you that better segmentation than doing something naive? Or
yes, that's something I should do, you're right. No, I've not the practical, but my intuition is that the topology is about noise, and relevance of how the modes are. The density makes guarantee that there is some sense in looking at these modes, and what you say is more about application. Yeah. I know I want to merge clusters that looks similar. So that's two different ways, and both, at the end, we propose to get both at the same time. You multiply the color difference by the persistence. Some details that I will go quick because we are running out of time. You can change the density function by something else, and the good thing to do is to apply a log of that to take into account the ratio of the density instead of the difference of density. As we just discussed, you can look into the color difference. You can do PCA on your feature space to reduce its size and go even faster. A few results. So we tried on a feature space which associate location and color. We run the Berkeley benchmark on it. We obtain the expected accuracy, which means that we are not better, we are not worse, and we are significantly faster. And when I say we obtain the expected accuracy, when there's a lot of color difference like this picture, we obtain a very good segmentation, as we can see here. But for something that is hard, like this tiger with a lot of camouflage, we fail. I think it's important to show that segmentation is...
How are we supposed to interpret the segmentation? Or is the black and gray different?
Okay, so the gray levels I will show you later. This is the persistence that separate two clusters, which means that this boundary here is weaker than this black boundary.
Okay.
I will just show... and so yeah, it works where there's colors, but it doesn't work where there's no color. And here, so the gray level indicates the persistence, and I will just show how it looks when... Here there's no extra computation, it's just for the video I sweep through the hierarchy and show that we go in coarser and coarser representation of the segmentation. And again, so here's that where I think it's interesting, for instance, for the sky to start to get very large cluster to analyze this picture. So the running times are interesting. So this curve here is the standard mean shift implementation by Command-HU. So and here that's time, and here that's the size of the bandwidth of the kernel that we use. So we can see that the standard implementation that works with points and iteration. As you use a larger kernel, it goes slower because there's more points to take into account. This point is a Fedson-Valp algorithm that works very fast. This is 18 seconds, and this picture is 8 megapixels. And it works fairly the same time any settings you apply to this algorithm. And all the other curves are algorithms with different settings. This one is a most conservative one with no simplification, compute the finest level directly, no PCA. And for instance, to give you a sense of all this curve, I think this one is the one you want to use in practice, where you use dimensionality reduction to remove one dimension. It's very safe and still improve a lot the computation. And you apply a weak threshold to remove the smallest clusters that are due to noise. And as we can see, very quickly we outperform previous techniques in terms of performance. And here an example on video. So our motivation was initially by this Michael's work on video processing, where it started to over-segment the result. So if we use a 5D feature space, we are somewhat in the same range. I'm sure that difference is mainly due to that we don't have the same machine. But we can be more aggressive on dimensionality reduction and get 40 seconds to obtain this result. So here's the input. And this is a typical example where the video camera we have is not so good. There's a lot of color quantization that occurs in this video. So it's interesting to first threshold remove the smallest cluster, as we will see. So that's the result with the 5D vectors. And next we will see the same segmentation with 4D vectors. And as you can see here, that's a very colorful scene, so there is almost no difference, but we gain an order of magnitude on the running time. So to conclude, on this part, I've shown you a topological interpretation of the mean shift algorithm, propose a way to build a hierarchy using topological persistence. This algorithm is not always useful. If you use small kernels, it's not very fast, but for large kernels, it's very useful. And it has the advantage to give you a hierarchy for free, and you can access on the fly any intermediate level. And a more general conclusion on my talk, I presented this fast and simple image processing based on the bilateral grid. And you can see the bilateral grid as a feature space where we associate X, Y, and intensity. I've shown you this image segmentation that is also fast and fairly simple using the feature space associating X, Y, and color. And an open question is, what else can we do with this feature space? It seems that these feature spaces are it's kind of a nice world where everything is smooth, every algorithm is simple, and all the sampling can be coarse. Whereas if you work in image space, you have a lot of samples and there's a lot of discontinuities. Whereas you move in feature space, you don't have any more discontinuities. algorithms are much simpler. It's Gaussian blur or just sorting pixels and counting your neighbors. So I think that it's a promising direction to look at. If there are other algorithms, we can find the right space to express these algorithms. So thank you very much.
Thank our speaker. Any other questions? Okay, well, thanks for coming.
Thank you very much.